introduce yourself to start.
My name is Michael Collins. I'm a senior 2 here at Kettering. My expected graduation is the fall of 2024. And for my MEC 322 fluid mechanics project, I designed a hydroponics plant system. A little bit of an introduction for what I wanted to accomplish for this project was to build a small-scale sensor readout hydroponics plant system that is fully autonomous in what it does. The idea is to grow healthy plants without the use of soil. What is hydroponics? A hydroponics plant system uses, instead of growing media of growing media of dirt, it uses water. There is no actual soil in the system. The water has dissolved plant nutrients in it. That's all the plants need to actually grow and be healthy. The other aspect of it that makes it desirable is it's a lot less susceptible to viruses and natural deterrents to growing. So in this system, there's room for 10 plants, and they live in these little pods. Instead of dirt, it uses spun rock wool and pea gravel for the root systems to grow, and the roots live here in the bottom, and they remain completely submerged. This system is also like a subtype of hydroponics. There are several. This is what's called a nutrient flow system. The plants are in a constant flowing state of water, so there is never a stagnant pool. This keeps the root systems clean, as well as constantly being agitated, where they will absorb more nutrients and grow healthier and faster. My personal interest in this is not the first time I've built a system like this. I have attempted a much larger scale and didn't work out so well, so I wanted to try it better, smarter, more efficient. That's why this one contains sensor control as well as generally just a smaller, more efficient setup. Quick, simple bill of materials. Most of the components are either 3D printed or off the shelf. You can get pretty much everything besides the electronics at a Home Depot. Come on. My process for how I accomplished this project was I did a lot of research on what type of system I wanted to build, how I wanted to build it. Then I started a preliminary exercise of what I call Crayola CAD, basically putting shapes on a flat wall and figuring out how I wanted to build my system. This particular version uses PVC pipes and again, the 3D printed brackets, so it mounts directly to a wall. This is my fake wall. A previous design I was going to use a storage bin where all the plants lived in a lid. I found that to be a little less robust and repeatable. Next stage, which was to just redefine the system, go through, make everything a little more detailed, and then start figuring out how to build it. So I made a scale model that was 1/10 scale, learned a lot of things about fitting 3D printed parts to PVC. After that, I actually started building the real thing that you see here, wiring all the sensors in, figuring out all the fitments, getting the PVC lines connected properly. And the last step, which is not actually complete, is to populate the plants and actually fill the system with the nutrient water. Part of the reason it's not populated right now is to create a plant specifically for hydroponics, takes a long time since you have to grow it without dirt. But the other aspect is you can't just put a seed in this system because it won't grow. So it takes a lot of time and care before it's ready to pop in. And that just takes time that I wasn't able to do for this class. So here's a picture of my CAD model. Things not pictured are the PVC lines. I just couldn't design all these little fittings properly to make it work nicely, so I just omitted them. The other picture here is my 1/10 scale model that I 3D printed. The biggest takeaway from this scale model was, we'll come back to that, the biggest takeaway was fitting. So these brackets that are pictured here and here didn't go nicely. They didn't want to fit properly because 3D printing itself is a process of extruding a thermoplastic through a nozzle, which deforms and changes the shape of it. So some testing had to be done. For the real full model, this particular bracket was reprinted twice because it was too tight on the PVC. So when I went to assemble it, it kept breaking. No. Do. Quick note for the 3D printing aspect of it. All the components are made out of PLA or matte PLA. They were all printed on a bamboo P1S machine at 15% infill with 4 top and bottom layers for strength, as well as 3 walls. I forget the exact amount, but the total filament was just over 1 roll, which is 1 kilogram. My design choices for this changed over time, but I knew after I decided to go with a wall-mounted system that I really wanted everything to be off-the-shelf PVC pipes. Another aspect I wanted to future-proof was there is a submergible aquarium pump in the bottom of this lower pipe, which is my reservoir. I wanted it to be able to be serviced in case the pump ever dies. That's what this big, large blue nut is a large threaded fitting so I could gain access to the pump if I ever have to change it or flush the system if, say, there was like a bug infestation and they were all in the reservoir. Other aspects I wanted to do was to assist with flow through the system. Both the what I call the plant troughs and the reservoir are canted at 5 degrees. This allows for a little bit of gravity assist to help with the water flow. It also increases the surface area at which the roots can contact the water. From research, I discovered that a lot of hydroponic setups that are nutrient flow use between 3 and 10 degrees of angle for the plant troughs. The other reason the reservoir is canted at the matching angle is so the pump has a greater surface area of being submerged. If I were to do this again for a second revision, I would make the angle up top adjustable, and I would make the angle below a much steeper angle, probably closer to like 45 degrees, to keep the pump more submerged. Lastly, the system was designed for wall mounting, as I've mentioned before. As you can see here, it's not mounted on a wall because it's hard to move one of those. But the idea was to have it put in, say, a back room in your house where it can just exist. This system can hold 10 plants. in these designed 3D printed pots. These are a little taller than your average disposable plastic pot, so it'll reach the bottom of the PVC. The reservoir also holds 1.3 gallons, so the overall volume of the system is slightly over 1.3 gallons. The sensors used were broken up into 3 types. I wanted to use a water level sensor, so again, to keep the pump fully submerged in case, from evaporation and the plant's absorbing water, I might not tend to this for several days. I don't want the pump to run dry because that will kill the pump. Second, probably the most important sensor is a dissolved solids. So it's not just tap water that runs through this system. It is dissolved plant nutrients that lives in that water to make the solution. This sensor will monitor that, so when I need to add more, it'll tell me if I need to add one of the other to balance out the mixture. This sensor also measures pH level, so if I have a slightly higher acidic water, I can add a base to it to even it out. Both the water level and the dissolved solid sensor are mounted in the reservoir, bottom base here. These keep it fully submerged, and it's also in like the beginning of the flow line. For future planning, I would mount the water level sensor higher in the reservoir. Oh, wow. Because where it's mounted now, if it's triggered, the pump is already not submerged. So that was bad placement. The last sensor is a flow sensor, which is mounted here on the fill line. This will help me keep track of how much water is constantly flowing through the system. With my pump, its maximum capacity is 2.6 gallons per minute, or 160 gallons per hour. This, I have the metric number. This pump measures 30 liters per minute, or not pump, flow sensor, 30 liters per minute. So it's more than adequate for what I'm doing here. All of these sensors go back to this electronics housing, which has an LCD display as well as an Arduino Mega inside to run everything. The pump is just a standard aquarium pump. It is AC powered. As before mentioned, it pushes 160 gallons per hour or 2.6 gallons per minute. It has a total lift capacity of 4 feet, so much greater than what I have here. This is good for future proofing because I can extend these plant troughs and move them higher. So they could be 5 to 10 feet long, and I can move them higher while staying within the capacity of this pump. The pump is also relatively small, so it fits inside the PVC. This picture is kind of dark, but this is this housing, and you can see the pump fitting nicely inside there. The 3D printed fitting that has the threads also incorporates a mounting spot for this size pump specifically. One of the biggest aspects of this is, well, it is a plant system, so you can't not talk about the environment. The biggest impact that this has is most farm fields, the soil is slowly being eroded from all the nutrients being pulled out of it. This system doesn't use any soil. It uses manufactured dissolvable solids. And it ends up being a much cleaner system than if you were to have a standard garden in like your backyard. It's a lot less fertilizers, a lot less potentially harmful chemicals and pesticides involved in the system. So I did fill it and I did run the pump for a period of time, and some of the aspects I learned from this was my return lines over here. I used 1/2 inch PVC. That was too small of a diameter. So what that does is down in here where it's supposed to feed back into the reservoir just with gravity, it's having a bottleneck and there is pooling liquid there. It's not substantial, but depending on if there's any debris from the plants or anything getting in from the top, that could clog and bottleneck my entire system, draining the reservoir and killing the pump. For future, the fix would be to increase that diameter to,
Here?
yes, increase the diameter of the return line
Oh, yes.
to unrestrict this flow system. The other thing I would do is instead of having it come off and then over and down, I would want it to come straight down. This extra pipe isn't necessary, and it's adding more room for the water to go. The reason it's here is complications with off-the-shelf fittings. Kind of already been talking about this, but the suggestions for the second revision, the biggest one is, in my opinion, the solving the flow. The second biggest, is the reservoir size. I think the reservoir needs to be larger to incorporate more solution into the system. With the current pump and the current volume of the reservoir, it is draining and refilling twice a minute. While it's good for the plants, it may not be good for longevity of the system. And the last thing I would really want to change for a second revision is sensor placement. That water level sensor is in a horrible spot. It would need to be closer to up here. The dissolved solid sensor I would like to push closer to the pump where it's at the very beginning of the run. Ideally, if I could get the probes directly in front of the intake of the pump,
Right.
that would be ideal. Alternatively, or not alternatively, another thing I would like to change is all of these PVC fittings. This is kind of unnecessary and unsightly. This is where the cable for the pump comes out, and it's not a very elegant solution. Also, this is siliconed in place, so you have to break that seal to get the pump out. For future, I would like to design an O-ring seal, so it's just plug and play. Any questions?
Yes, outstanding, outstanding design. Can you talk about the potential for commercialization, as we talked before? Can you talk about that aspect of your system?
Yes. So one of the biggest things I wanted to do was to make this almost a DIY-able system. So all of the 3D printed components take up the complicated geometry. So like for example, the 5-degree angle that is built into these parts, as well as all these fittings on the end and these brackets. So these brackets that hold up the pipes can be mounted level and plumb to a wall, but then when you insert the pipe fittings, this creates the angle. So, and like these, which are more cosmetic than function, these return the spot for the plant troughs back to level with the wall. So all of the white components are off the shelf that you can buy at a Home Depot. So if this was sold, this is the only one removable. If this was sold as a, say a plans kit with 3D printable files, you could print all of the components on a relatively cheap DIY printer for less than $30. All the printed parts could be made, and then all of the PVC is off the shelf, cut to length, and put in. The sensors are also very cheap Arduino-based sensors. So everything is DIY-able for this system. It makes it great for selling digital plans as well as selling a weekend warrior kit. It's also a very scalable system. The reservoir and the plant troughs can be extended. In this example, they're 24 inches long, but you can make them 60 inches long relatively easily.
Right. And so, in terms of volume of the reservoir, the volume will be a function of how many troughs you will have on every level, right? And so, as you add, so is it more efficient to add more troughs or add more levels? No, more troughs or simply add more levels of troughs?
I would say the simplest solution would be to add length. Length of the plant trough, so extending it this way as well as extending the reservoir.
Right.
Having multiple levels means that the pump is going to be pushing higher distances and it's going to be
Operating in
splitting.
parallel.
Yes.
Yeah, I can see that adding more levels would increase the volume flow rate of the pump required, because you have to pump higher and also more levels. But adding more distance per level increases the pressure drop.
Yes.
Yes. Yes.
The way I mentioned in the beginning,
Yeah.
this is not the first time I have designed a system like this. The way we did it for what I really was Rev 0, which was 4 levels.
Right.
We took the pump, put it to the top, and it gravity fed down to each level.
Okay.
This resulted in the top level being overpressured,
Yes.
the second and third level being close to ideal, and the bottom level being starved of water.
But did the pump provide the flow in parallel to each
No.
level?
No, it did not.
Yeah, see, and I would really think that the pump should provide the same amount of flow for every level. Okay, in parallel. It comes up, and it feeds every level, and it is collected at the end and goes back to the reservoir. You know, if I was just doing it from fluid dynamic standpoint, I can imagine it would require a larger pump, more flow rate, but every trough though would be assured to have the same volume of nutrients every cycle.
You mentioned larger pumps.
Yeah.
This size
Yeah.
is very scalable. The dimensions of this pump are standard for aquariums.
Yes.
So you can get anything from 80 gallons per minute to 900 gallons, or 80 gallons per hour to 900 gallons per hour
Yes.
without changing anything. It's just plug and play.
Yes.
That was another one of my main aspects of picking the pump I picked.
Excellent. Yeah. So I would. Yeah. Because if you have the pump capacity, multiple levels, and providing equal flow for every level is I would think the best way to do it for sure. Okay. Well, so what did you learn overall from the project relative to fluid mechanics?
So the first revision of this project that I built with a roommate of mine failed.
Right.
And the biggest aspect of why it failed was the pump. Picked the wrong pump and it didn't have enough flow. So what this project really taught me how to do was to pick the right pump for the job, as well as one thing I learned while building this version was basically having to get the water out of the way with the drain lines not being correct. This is something I would change in the future, and now it's something that having to get things out of the way is something I will carry with me as a lesson.
Because you need to reduce the pressure restriction at the end
Mhm.
to allow the fluid to flow from the plants out of the system into the reservoir. Okay. And so, yeah, so you can do that by having a larger pipe size here. Yeah, so a larger pipe size. Okay.
Because you're pushing through half-inch PVC
Yes,
up to
half-inch.
3 gallons per minute.
Yeah.
And that's not in hindsight, not the best idea.
Increased pressure drop.
Yes.
Yeah.
So those are the main, biggest takeaways I have from this project. There's a lot of little 3D printing things that I learned, but those don't 100% pertain to what we learned.
Well, I think that you've done an outstanding job. This is actually a great project. It meets all of the requirements that I look for a project in fluid mechanics. Okay, and I just hope that it didn't require too much of your time, and take away from other classes. But you for sure have learned quite a bit, and you'll be able to apply the concept from fluid mechanics to other divisions as you seek to improve the overall performance of your project. So, do you have any questions for me?
Not any immediate specific questions.
Okay.
I do, when I work on the second revision, I would like to pick your brain a little bit on the, more specifically this issue
This
that,
issue here.
yeah.
Okay, here's the question. Do you think that the project should be required as opposed to optional?
So I'm not, personally, I'm not a very, I guess, layman's terms, book smart kind of person. I'm a very hands-on person. So when you presented a project option, there was the final exam option I was not doing that. I think I learned way more from doing this project than I would just sitting studying,
Right.
as well as earlier in the term when we did the flow lab, I learned way more during the flow lab than honestly any lecture.
Mm-hmm.
Simply because I could get here, I could hold it, holding the pitot tube and going, when you put the pipe here, this is the reading you get, and you take this number and divide it by this number,
Yeah.
this all makes sense.
Right.
Watching it on a slideshow, for me, I struggle to retain.
Yeah.
But physically building it, I'll never not know how to pick a pump for a system now. So.
Right. Okay, good. Okay, well, great job, and so let's go ahead and finish up the exam. So thank you very much for all your time and all your hard work. Okay, great.